So in our last discussion, we learned about geospatial database processes. Two distinct components such as locations and attributes, they are associated with spatial databases. The geographical features in the real world are very difficult to capture and may require large-scale databases, which might be very voluminous also. So this spatial information science can organize reality through the data models, where spatial phenomena databases is structured in the form of grid and square or rectangular cells. Then the representation is generally called as the raster data, which we have looked into in our previous discussion. In this part, we would look into another data format, which is vector data format. If you recall, we explained that vector data format represents specific features on the Earth's surface and assign attribute to those features. And these vectors are composed of discrete geometric locations represented by XY values. They are also known as vertices that define the shape of the spatial object. The organization of the vertices determines the type of vector that we are working with. It can be point, it can be line, or even polygon, which we may also call as area. Just to emphasize again on the main difference between raster and vector data is that the raster data represents as a cell or a grid matrix, while vector data represents data using sequential points or vertices. That's what the major difference between raster and vector data, which is very clearly evident in this diagram also, which I am presenting before you. So if you see here, a vector data structure represents the use of spatial objects with a physical quantity that requires both magnitude and direction of its description. The vector data, if you see again in the diagram, comprises vertices and paths with three basic symbol types, including point, line, and polygons or areas. All of them, they are represented by vertical points. A point is specific location which is specified as XY coordinate in the Cartesian coordinate system. In geographic coordinate system, we may call it as latitude and longitude, the XY coordinates. Similarly, a line is represented by a sequence of connected points known as vertices. And the polygon, a closed area specified by a polyline having the same starting and ending point. So this you can see here in this diagram also, that how vector data can be represented in the form of point, in the form of line, and in the form of area. And all the vertices have specific XY coordinate locations which represents the ground coordinates. So here vector data, it is familiar with coordinate geometry representation of a specifying point line or polygon by two-dimensional coordinates because of the assumption that the real world can be divided in clearly defined elements. So a point has one XY coordinate, if you can see here in this diagram also. A straight line has only two pairs of XY coordinates, whereas a polyline, if we have two lines over here, then they will have more than two pairs of XY coordinates. And the area feature will have a combination of line segment having common starting and ending point. For example, if you see here, the vertices would the line vertices would start from here, then it will come and end up here all again. So here we need to understand that the selection of appropriate number of points for the construction of an entity is an important step, as too many points will cause repetition and too few, if we have lesser number of vertices, then it will lead to overgeneralization of the feature. So we have to make compromise between these two. Neither we should have more number of points, I mean to say more number of xy coordinates to represent any vector information, vector spatial information, either it is line, polyline or area, because the point data will only have one xy coordinate. But if we are representing line or polygon information, spatial information, then we should be very particular that we should not have many vertices, because that will lead us to having more repetition of xy coordinates, and if we reduce it, then the map or the area which is being represented would be generalized a lot. So we have to make adjustment, we have to make compromise depending on our requirement. In addition, we also need to remember the significance of attribute data. The spatial data are where the things are, and attribute data are the attribute data represents what the things are. So attribute is actually depicting, representing the attribute information, the features of that specific geographic coordinate, whether it is point, it is line or area. It means attribute data attaches quality to the spatial data, because that is what our objective is. It is our objective is not to present any map. We want to present the spatial information where we want to add the features, characteristic of that specific location, and in that context attribute data is very important, since all the information cannot be represented by geometry alone. If you see here, it is only this diagram is showing only the geometry of it. We do not know that what polygon 1 means, what polygon 2 means, and what line 1 means, line A, B means. So that way all these information cannot be represented by geometry alone. Therefore, it becomes necessary to attach the quality, the attribute, the name, number, etc. It describes some aspect of the spatial data. So here we can notice the naming of lines and polygons, which are very important and critical when we are bringing the vector information into the spatial data format. Moreover, feature classes can be structured as layers or themes in the databases, which we have discussed earlier also. Or feature class may be linked to an attribute table. Now, when we are linking the attribute table, then we may be drawing the attribute information and incorporate it into our spatial information into vector format or raster format also. But here we are discussing about the vector format. So every individual geographic feature corresponds to a record if we are linking it with the table, record in the row within the attribute table. So this is the spatial data is used for different analysis of the region, remains unchanged, whereas the attribute keep on changing as per the requirement. So this is what the basic feature of attribute information which is associated with any spatial data. In this case, we are representing it in the case of vector data. Since most of the thematic mapping is for spatial information system, they are based on polygons. Their storage and manipulation has received considerable attention. The characteristic of polygon is that it must have a unique shape, area and perimeter. The representation of a simple polygon with a few points is straightforward, but it becomes very complex when more such polygons or two or more such polygons are stored. The adjoining boundaries may enter twice. This may cause into duplication of adjacent line and create matching problem. It also makes data voluminous. To overcome this and the related problem, there are largely two models. First one is the spaghetti model, spaghetti data model. They are also referred as non-topological or path topological model. Now, as the name spaghetti suggests, it is direct line-by-line translation of a vector map. In the spaghetti model, each entity, for example, either it is point or line or area, becomes a logical record in the digital file, and it is defined as string of xy coordinates as we have seen earlier. Second is the topological model, where topological data define the logical connection between point, line and areas for geographical description and analysis. And that way, topological model, they are more applicable for spatial analysis, but they are voluminous as well as they are a little difficult to manage and incorporate into the spatial information. So, but they are actually represents the spatial information much more effectively in the spatial analysis. Now here you can see in the three diagrams which I am showing you about the vector spaghetti data model. However, the simplest vector data model stores and organizes the data without establishing relationship among the geographic features are called as the spaghetti model. That is what we have discussed in our previous slide. So, highlighting the spaghetti model, I would say that spaghetti model where lines in the database do not overlap. Even if they overlap, they do not intersect, just like spaghetti on a plate. The polygon features are defined by lines which do not have any concept of start and end node or intersection node. So that way this spaghetti model is very basic in nature, but this is one very easy way to represent the spatial data in vector format using the spaghetti model. So in spaghetti model, there is no data attached to it, and therefore no data analysis is possible in the spaghetti model. No data means no attribute data is attached to it. So this is what the spaghetti data which you can see over here. Now, in contrast to the spaghetti data model, the topological data model is characterized by the inclusion of topological information. You recall we have explained earlier about what we mean with topology. Because the topology is very important in the context of spatial information, because that gives us exact idea of any spatial phenomena over the Earth's surface, the relationship with its surrounding. So when we are representing this ground reality in the form of map, in the form of spatial data, the attribute which is linked to the spatial data is very important and critical to know its exact position and its also surrounding phenomena which are attached to that specific location or point, line and area entity. So I was saying that the topological model is characterized by the inclusion of topographical information within the data set. As the name implies, topology is a set of rules that the model the relationships between neighboring point, line and polygons and determines how they share the geometry. Now that's very important and significant in the context of topology. For example, consider two adjacent polygons. In spaghetti model, you have seen that the shared boundary of two neighboring polygons is defined as two separate. If you just, if I can go back to the slide and I can show you. So here you see this is in spaghetti model, the common lines are being digitized again, are being incorporated in the spatial data again. So these common boundaries are not the common boundaries. That's the point which I want to make. So we are saying that two adjacent polygons in spaghetti model, they shared the boundary of two neighboring polygons is defined as two separate identical lines. The inclusion of topology into the data model allows for a single line to represent this shared boundary with an explicit reference to denote which side of the line belongs with which polygon. So that's an interesting point which I want to make in in connection with the topology model. So topology is also concerned with preserving the spatial properties when the forms are bent, stretched, or placed under similar geometric transformations, which allows for more efficient projection and reprojection of map files. All in all, I would say that topology model is ultimate of the spatial information science representation, the spatial representation, because we have seen in our previous discussion that raster data also have some kind of there are some errors which are associated with some of the properties of raster data. Similarly, within the vector data also, the spaghetti model has certain deficiencies, but topological model, I would say, is having far lesser discrepancies, far lesser errors there in the topology model. So I would say in modern day spatial information, topology model within the vector data format is ultimate and is well accepted by everyone. Now this diagram is showing you how the spaghetti model works. The image clearly depicts the difference between spaghetti and topology data model. Now, we have discussed about vector data, we have also discussed about raster data. So what is the outcome of the choice between raster and vector data? You see, if you look into this table, you would find that there is some kind of comparison which I have made between raster and vector data depending on the data collection, data volume, data structure, geometrical accuracy, graphic treatment, area analysis, network analysis, generalization. On all these counts, mostly the vector data would be better off. Yes, to incorporate, to bring the ground realities into the vector data would be slow, the data volume would be larger, but overall, for the purpose why we are using the spatial data, vector data would be preferred model for spatial information. But here I would also like to point out that you see in modern day, most of the sources of spatial information, I mean to say the satellite imageries, remotely sensed data, they come in raster format. So there the compatibility is more with the raster data rather than vector data. So why I am saying this, that when most of the time, many a times we also use vector data for the digital images also, which comes originally in raster format. So when we convert them into vector format, some errors might come, some errors do come, which we have to manage, which we have to rectify the errors. So this issue would always remain as to what would be the better option for using raster or vector data. To sum up, I would say that it all depends on the user and the kind of application, the kind of processing we want to make for the we want to make the processing in spatial analysis. That would be important. If I can give you one example, for example, area analysis, raster would be better. For network analysis, the vector data would be better. So argument about which is better between raster and vector model depends on the purpose and usage. Raster databases are appealing because of simplicity of organization, speed of many operations, for example overlay, buffers, and especially appealing to the remotely sensed information. So that way raster data is very good, is very efficient. On the other hand, there are many situations in which the raster approach may appear to sacrifice some of the details, and that is why for example, the cartographers are appalled by the crude outlines of parcels that resulted in the pinking shear effect of diagonal boundaries represented by grid cell edges. For example, we discussed it in our previous discussions as to how the grids and the area coverage, when they are being overlaid and it is not covering the entire grid, then some errors might come, which we have seen in our previous discussion. Similarly, the inaccuracy caused by the cells when portraying linear feature and points and situations in which raster approach sacrifice too much of detail, that also is one very big challenge in incorporating real ground information into the raster format. However, the computing times of overlaying vector-based information can be excessive, and polygon overlay routines are error-prone, expensive, and slow. So all in all, I would say that it depends on our choice as to which one would suit to our requirement, which one would suit to our analysis. This is what the comparison between the raster and vector data model. You see, the advantages of vector data model lies with the compact data structure. As I have said, that network analysis is very efficient there. And also when we are transforming the projections, that there also vector data model is very appropriate. And final map output, it appears very neatly drawn lines are being represented through vector model. Whereas if you see the raster model, they have simple data structure. It is very easy and efficient for overlaying. As I have said, it is compatible with remotely sensed imagery, simple for programming, and same grid cells can represent several attributes, so that's all are advantages. Among the disadvantages of raster data, the errors in perimeter, shape, loss of information, these are very important disadvantages of it. Whereas the disadvantages of vector data includes they are complex as well as they are voluminous data. This is again, I would say, example of how data structure is represented in vector and raster data. The storage, the same is being presented before you, specifically with specific property and how vector and raster data is appearing in spatial information. All in all, I would say that it is a tug of war between vector and raster data format. It depends on the requirement, it depends on the efficiency of drawing the spatial data into spatial data into our analysis and how efficiently we can process it.